A sealed physics detector was calibrated at 1200 counts per minute. Later, its display reads only 150. Nothing is leaking, and the instrument is healthy. The signal itself has faded. The missing label asks one question: how much time has passed? If the source lost the same number every minute, a straight line would solve the mystery. Radioactive populations do something different. During equal time intervals, they lose the same fraction of what remains. The amount removed keeps shrinking, so subtraction is the wrong machine. One nucleus decays at a random moment. A large crowd is predictable. After one half-life, about half remain. After another, half of that remainder survive. Physics cannot name the next nucleus, but it can forecast the population. That repeated fractional change is the signature of an exponential. Start with n0 nuclei. One half-life multiplies the population by 1/2. Two half-lives multiply by 1/2 twice, leaving 1/4. 3 leave 1/8. The exponent records how many equal time multiplication cycles have occurred. N equals n0 times 1/2 to the power t over t1/2. Time does not jump between whole half-lives. Halfway to the first mark, the exponent is 1/2, so the multiplier is the square root of 1/2. Fractional exponents fill every gap consistently. The staircase of repeated multiplication becomes a smooth decay curve without changing the rule. The same machine can grow. A multiplier above 1 raises the curve, a multiplier between 0 and 1 lowers it. The initial amount sets the starting height. The base controls the fractional change per chosen interval. Change the interval, and the numerical base changes, but the physical process does not. This is the visual test. Move one equal step to the right. A line adds the same vertical amount. An exponential scales its current height by the same factor. Near the beginning, the change may look gentle. Later, it can be dramatic. Equal horizontal steps create equal ratios, not equal differences. Half-life notation is convenient, but nature does not wait for checkpoints. Slice time more finely. In each tiny slice, remove a tiny fraction proportional to the slice width. Double the number of slices and adjust the multiplier. The stepped predictions settle toward one continuous curve. That limiting bookkeeping introduces the number e. It is not a decorative constant. Base e is the natural language for continuously compounded fractional change. We write n of t equals n0 e to the minus lambda t. Lambda is positive, and the minus sign tells the population to decay. Lambda has units of inverse time. A larger lambda means a faster fractional loss. Its reciprocal, tau, is the time constant. After 1 tau, the remaining fraction is e to the minus 1, about 37%. Half-life and time constant are two clocks for the same curve, related by t1/2 equals the natural log of 2 times tau. Notice one more physical clue. Where more nuclei remain, more can decay during the next moment. The curve therefore falls fastest when it is high and slows as it empties. Later, calculus will compress that idea into a slope proportional to the current amount. For now, the motion is the meaning. The exponential moves forward. Give it a time, and it returns an amount. Our detector asks the reverse question. We know the amount and need the hidden time. A logarithm is the operation that reads an exponent backward. The statement b to the x equals y and the statement log base b of y equals x contain exactly the same relationship. One asks for the output, the other asks for the exponent. For base e, we write natural log, or ln. Exponentials and logarithms undo each other. Return to n equals n0 e to the minus lambda t. First divide by n0, creating the remaining fraction. Apply natural log to both sides. The log cancels the exponential, leaving natural log of n over n0 equals minus lambda t. Divide once more. T equals minus 1 over lambda times that logarithm. Why can the logarithm expose an exponent? Powers turn added exponents into multiplied factors. Logarithms reverse that translation. A product becomes a sum, a quotient becomes a difference, and a power drops in front as a multiplier. These are not separate rules to memorize. They all say that logarithms measure multiplication in additive steps. Physics adds one safeguard. Never take a logarithm of a measurement carrying units. The ratio n over n0 is allowed because the units cancel. A logarithm needs a dimensionless number. Writing the ratio is not cosmetic. It keeps the equation physically meaningful. Real measurements arrive as noisy dots, not a perfect curve. Plot count rate against time, and the exponential bends. Now keep time horizontal, but replace the vertical coordinate with natural log of n over n0. Every measured dot moves. The curved pattern straightens into a line. The line follows natural log of n over n0 equals minus lambda t. Its intercept is 0 after normalization, and its slope is minus lambda. A straight line fit therefore measures the decay constant. From lambda, we recover the time constant and the half-life, even when individual readings wobble. The detector is only one member of a family. Voltage on a discharging capacitor falls exponentially. Light intensity fades through absorbing material. A damped oscillator carries an exponential envelope. Different mechanisms supply different constants and units, but the same exponential describes forward change, and the same logarithm reveals hidden time or distance. Our detector fell from 1200 to 150 counts per minute, 1/8 of its initial reading. 1/8 is 3 successive halves, so 3 half-lives have elapsed. The logarithmic calculation gives the same answer even when the ratio is not a convenient power of 2. Keep 4 connected ideas. Equal intervals with equal ratios create exponentials. Base E describes continuous fractional change. Logarithms recover the hidden exponent. Logarithmic axes turn exponential data into lines we can measure. These are not symbol tricks. They are tools for reading clocks, distances, rates, and scales from the physical world.